All right. Good morning, everyone. Welcome back to Math 154, Week 3, Lecture 2 on this wonderful Monday morning. Your friendly reminder that you are supposed to always read ahead one section. So we had finished Chapter 1 last time, which means hopefully you put your eyes on material from 2.1, whether it was the notes to share, the e-text, or both. I would prefer that you definitely look at the notes to share, the next section before class. And then I had said it's also a really good idea to look at the textbook as well, not read in full detail, just check it out so you have an idea what we're going to cover. Which today we'll start our very, 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 very long journey into ratios. Another friendly reminder that you should practice stuff with Excel over and over and over. Don't just do it once and think you have it memorized. Repetition is definitely key. We showed you how to make that addition or multiplication table in class previously. I specifically showed a multiplication table, but you could make an addition table for practice as well. It's pretty much the exact same thing. And that was for good practice using fixed cell references between fixing a row or fixing a column, because that's going to start being necessary once we hit 1.8. The Excel for 1.8, which is the BMI file. It's not going to be in every Excel homework in the future, but it will be in a decent amount of them. And we said that the multiplication table or addition table, if you choose to make it, you know what the answers would be in it. So if you do something wrong in Excel, you'll be able to tell. Whereas if you just do the BMI homework, you're not going to know the answers to that table off the top of your head. So it'll be harder to predict. Friendly reminder on due dates of stuff coming up, one new thing. So 1.1 is due today. 1.2 and 1.3 is going to be due on the 2nd, as well as week 3 lecture 1's discussion board also due on the 2nd. You also have that Excel heart rate file due on today. Remember, you have 6 attempts for that. All the other Excel files will be 5. And then the new Excel homework to work on after that will be TV loan 1.3. And that's going to be due in a week on the 7th, so 5 attempts. And when we covered that layaway problem in a previous class, I had said there was going to be a homework that was similar, not the same, but similar to it. And this is the one. TV loan kind of sounds like the layaway problem. But there's one major difference in this problem versus the one we covered in class. One of those two, there are payments involved, and the other, there wasn't. So in other words, if the one we did in class didn't have any payments involved, hint, wink, nudge, maybe this one does. So there's just an extra layer of detail, but you're not going to have to build it from scratch. It's going to be more like the heart rate, where it's just fill in the answers, or type a formula or two, fill things down. Maybe there's a chart you have to do, maybe not. Some homeworks don't have charts. And then just another friendly reminder to not wait until the last day to try homeworks. I'm seeing several students that have not even downloaded the Excel homework yet for the heart rate. I can tell when you've downloaded it. So please, please, please don't wait till the last day to do these homeworks, especially if you're waiting until the last hour and then you have no idea how to do anything. That's just a terrible idea. Put your eyes on it as soon as I tell you it's going to be due in a week. Oh, okay, so this is what I'm going to have to do. And then another day later, you come back to it and start working on it. Maybe you're stumped, but then a day later you come back to it and something clicks. So you have multiple days to check it out. I know some of us work really good in the clutch at the last second, but it's not always the best idea for most people, even though we think it might be, especially with something like this where you might be out of your comfort zone. Okay. So, like I said, we are going to begin chapter 2 today. We're going to start with 2.1, talking about ratios. We'll build up to proportions. We'll expand on these concepts greatly. We'll use them in lots of real world types of problems over the coming weeks. But chapters 2, 3, 4, and honestly, even 5 really all have to do with this material as its baseline. So buckle up, strap in, and let's go ahead and begin.
Let's get into chapter 2. And chapter 2, chapter 3, and chapter 4 are all very, very, very heavily tied to each other. Chapters 2, 3, and 4 are all very heavily tied to each other. Now, in fact, the rest of this course is very tied to chapters 2, 3, and 4, but we start expanding in bigger ways once we get to chapter 5, but let's not get there yet. We don't want to jump the line too soon. So ratios and proportions. This is an idea that we're going to study and discuss over and over and over and over and over. And we can approach this concept in a very simple way. We can take it one step further, and then we can take it another step further. So the simplest way is where we talk about setting a fraction equal to a fraction and cross multiplying to solve. That's the simplest way. What we can do after that is turn it into an equation involving this y equals kx that we'll see later. And then the next step is taking the idea of proportions and creating equations with them where they're not actually proportional. The idea of being proportional is there as a base, but there's something else going on. They're maybe inversely proportional or proportional with a square or a square root of something. So again, that very base idea, we're going to extend and extend and extend. But remember, we're taking this slowly. So let's start out with something small first. What is a ratio? A ratio is a way of comparing two sets of data that vary with each other. So specifically, when we talk about the idea of a ratio, sorry, I'm getting my colors set up. Ratios are fractions. Ratios are just fractions. The word ratio has the root word rate inside of it, and you'll hear that word described with fractions as well sooner than later. So whenever we talk about ratios, we're talking about setting up fractions. So a ratio is a way of comparing two sets of data that vary with each other, something like apples to oranges. And in fact, let me just bump some of this down that we don't need to see yet. TMI right now, there we go. A little less TMI, a little less I guess. So when something follows a ratio, it means that if one of these values is going to go up, the other has to go up as well. And they're going to go up in a similar fashion. It's not one of them goes up by 1 and the other goes up by 5, and then the next time the first one goes up by 2 and the second one goes up by 3. That wouldn't be a proportional relationship using ratios. A proportional relationship would be like something increasing by 1, thing 1 increases by 1, and then the other thing increases by 2. Then if the first one increases by 2, the second thing increases by 4. There's a multiplicative or divisive relationship between them. So data that is proportional will see one increase as the other increases, and thus can be set up as a ratio. So if your apples go up, your oranges go up. That means that the data is likely proportional. Now I said likely because just because these two things go up together doesn't mean they're proportional. They have to go up in a similar relation every time. And we'll get into a very useful, I don't want to say trick, but a way of telling if they're proportions ultimately. So when you're doing your homework, most, if not all of these problems, you're going to be told, hey, these things are ratios, these things are proportions, which means as one thing goes up, the other goes up in a similar manner. But in the real world, which is what this quantitative reasoning class is really all about ultimately, it's not just getting math problems right in a homework set, it's about extending these concepts into the real world for your own personal use. So in the real world, you may need to ask yourself if something is proportional. So what you do is you ask yourself, if one value goes up, does the other have to go up? And again, there would be a specific numerical relationship between those, which we're going to get into. But that's what you would ask if you think that two things are proportional. So you're running a store and you sell apples and oranges, and you think that there's a proportional relationship between the amount of apples you sell and the amount of oranges you sell. This is what you think. So you'd ask yourself as the store runner or manager or whatever, all right, when my apple sales increase, did my orange sales increase? And then on top of that, if you say yes, then you say, all right, well, is there a relationship between these numerical increases? Now, again, when you're doing your homework, when you're taking your tests, this is not really the main issue. It's not you asking if they're proportional. It's you'll be told that they are, and you go ahead to the mathematical relationship. Again, this highlighted statement is more real world scenario stuff. Also, discussion board level stuff or things from the guided worksheets more specifically. So when we're talking about those, again, those guided worksheets are more like us in the real world, if you will. So this idea will come up as we'll see. Now, when you actually get to the solving of your proportions, there is a main trick that I am going to always do, and I suggest that you always do as well. I highly suggest it. I would demand it, but it's hard to demand things when I can't watch over your shoulders constantly, right? So just pretend that I demand this of you. Write your ratio in words for consistency. Use your words. I can't tell you how many people make mistakes with these because they don't use their words, because they don't want to take the extra 10 seconds, and that's it, to write apple over orange or miles over gallon or students over teachers or pens over, I don't know, elephants, whatever the two things you're comparing. So please, please do that because it will save you a lot of hassle over time. Why is the highlight not going away? There we go. All right, so what do I mean? So let's say you have this problem involving apples and oranges, and you either discovered that they're proportional or you are told they're proportional. Then you would write apples over oranges. This would be the first thing I would do before injecting any numbers and solving any equations. And it doesn't have to be apples and oranges. You could be just comparing some random first thing to some random second thing. Pennies to quarters, students to teachers. Does it matter which one you put on top? In fact, no. And that's the whole point of this. That's the beauty of ratios and proportions, is that when you're dealing with proportional relationships, you could write apple over orange, or you could write orange over apple. You just have to be consistent. Writing the words out top over bottom is going to tell you where to put your numbers. So if student A, all right, so say we got a problem with 2 apples and 3 oranges. Student A writes 2 over 3 because they wrote apples over oranges first in terms of words, but then student B might write 3 over 2 because they chose to do oranges over apples. That's perfectly fine because when they set up the rest of their proportion, they'll continue to do whichever they said they're going to do, apples over oranges or oranges over apples, and everything will be okay. Again, it's consistency that is key. Monday over Tuesday, week 1 over week 2, scenario A to scenario B, however you want to do those. So you're going to be setting up equations where it's a fraction equal to a fraction. A proportion is an equation where it's a fraction equal to a fraction. That's our first idea of a proportion. A proportion is a fraction equal to a fraction. Yes, there's another way to write those out as equations. That's phase 2. We'll get there another day. For now, a proportion is what? A fraction equal to a fraction. It's a ratio equal to another ratio. It's the ratio of apples to oranges in the first scenario to apples and oranges in the second scenario. So again, a proportion for now is a fraction equal to a fraction where your units, words, ideas, concepts, items, whatever you want to call them, are consistently the same on the top and the same on the bottom. How do you solve these? This is something you should have seen before in a previous math class. This should be a reminder, but if not, here it is. You cross multiply to solve a fraction equal to a fraction. So your proportions starting out will look like this. A over B equals C over D, where A, B, C, and D would be numbers given in the problem. Maybe 3 of these would be numbers and 1 of them would be missing in general. So again, typically 3 of these would be numbers and 1 would be an unknown, and you would be able to solve for it by cross multiplying. Cross multiplying means to take the top of one and multiply it by the bottom of the other. And then you set it equal to the exact opposite pair being multiplied, the bottom of one times the top of the other. So you would get, sorry, I went blank for this. This is just me saying I'm changing the equation to this thing. I've done some math. The A times the D That was multiplying the top left and the bottom right. Set it equal to the b times the c. That's how you solve a proportion. You cross multiply, top left times bottom right, set it equal to bottom left times top right. If you swap the a and the d, nobody cares. If you swap the b and the c, nobody cares. It is this idea right here that makes it so it doesn't matter whether you did apples over oranges or oranges over apples as long as you're consistent. Because the whole idea of the tops and bottoms are going to go away, there's not going to be any more fractions once you hit this point. So if you did apples over oranges, you're not going to be able to tell that anymore once you hit this point. If you did oranges over apples, you're not going to be able to tell that anymore once you hit this point. And when you solve, if you don't make mistakes, you would get the same answer either way. So it doesn't matter whether you do apples over oranges or oranges over apples. Once again, I'm just saying this over and over. You have to be consistent. As long as you're consistent, the order you chose, apples over oranges or oranges over apples, doesn't matter. Just be consistent. All right. So we already said this. A proportion is two ratios set equal to each other. A ratio is a fraction. So that's no surprise what we just did up there. Couple small little memos that will pop up here and there, especially in the guided worksheets, as you will see as we work together. Very often we'll want to scale something to 1. This can be used in model scaling. This can be used in the idea of just trying to get a simplified or reduced number. This can be used in a lot of ways. And we will, again, be diving into this concept of scaling something to 1. But when you want to scale something to 1, you will make the requested value 1 and then solve the proportion. So you would be maybe told, all right, 2 apples to 3 oranges. And then they say, scale the apples to 1. So 2 over 3 would be one of your fractions. And then on the other side, the apple on the top, assuming it would be apple on the top, would be 1. So again, if I had something like scale 2 apples to 3 oranges to 1 apple, you'd have 2 over 3, because we're going apple over oranges, equal to, and because I said to scale the apples to 1, we'd go 1 over x. This would be our unknown. So the 1 is where the apples were. If I said to scale the oranges to 1, then the 1 and the x would be flip-flopped. So they generally tell you what to scale to 1. If for some reason they don't, some people will say scale the smallest to 1, some people will say scale the biggest to 1. What I find is most common with this course is that you scale the second value to 1. So if they don't specify which one to scale, it's generally going to be the second thing that they said. And as I said, we will see these issues addressed with the guided worksheet activities we'll be covering. How many times have I said this now? I just like to inject these statements again every now and then. I'll put those fixed cell references back up at some point. But remember, when you're doing things in this course, don't just do the math and move on. When you get an answer, ask yourself if the answer makes sense. When you're doing your work, read the question carefully, read it again, pay attention. Make sure you're using your words. All of these things are super important. Being detail, what's the word I'm looking for? Detail oriented? That doesn't sound right. Detail-minded, whatever that word is I'm looking for, paying attention to the details is extremely important. And we know nobody's perfect. Your teacher makes mistakes. You will make mistakes. But when you pay attention and ask yourself if things make sense, we often find those mistakes and fix them. I make lots of mistakes, but I get answers that don't make sense. I go back and find the mistake, and then I fix everything because I choose to pay attention. I choose to take my time, be detail oriented. Yeah, that was right. I don't know why it just sounded weird at first. Okay. Before we get into this proportion table, let's actually go ahead to the guided worksheets, and we are gonna, oops, wrong window. There it is. Nice little summary. You can read this on your own. We don't have the time to get into all that detail, but it talks about the main point of this is how in 2017, the number of US births was 3.8 million. And in 2017, the number of Mexico births was 2.3 million, again, rounding out. So you might say, oh, well, the US had way more births, but well, that might be true in an absolute number, 3.8 million versus 2.3 million. What we want to do a lot of the time is think of this as a proportional relationship. Think about this as a relationship to the size of the country. So we had 3.8 million births, but what was the population that year? Mexico had 2.3 million births, but what was the population that year? What is this growth, these births, in comparison to the original population? So Mexico had a population of 129 million people, whereas the US had a population of 324 million people. So the US has about, I'm rounding, 3 times as many people, and yet their number of births, 3.8 million versus 2.3, is not 3 times as many. If they were, this would be in the 6 or 7 million ballpark, but it's about half of that, roughly, the 7 million, that is to say. So this isn't really a proportional relationship when you wanted to just say, you know, US to Mexico versus their birth rates. When you look at them as singular proportions, the US alone and Mexico alone, you can see that there's 11.88 births per 1,000 people. So this is a very common type of proportion where they compare it to a per 100 people or per 1,000 people, as we will see moving forward. So there was about 12 births for every 1,000 people in the US, but there was about 18 births for every 1,000 people in Mexico. And what that means is Mexico is growing quicker, at least in the year 2017. They have more births in this sense when you think about it as a base value of the population. Then they mentioned that only women of childbearing age can have babies. So of course, maybe we should be comparing births to the number of these women instead of the entire population. Men can't have babies. Women that are too young or too old can't have babies. So they say maybe we should just be looking at this as a relationship or a proportion to the childbearing aged women. So that's another important concept. How are we comparing these two numbers, our apples and our oranges? Does it make sense to compare the number of births to the entire population, or would it make more sense to compare the number of births to the childbearing aged women? And that's something that we can study in a real world quantitative reasoning sense. All right. One of the few times where I will just annotate on this, just to keep things simpler so I don't have to type in another screen and keep going back and forth, but I'll have to erase it ultimately after this page is done. But you've got the video to review if you need it. All right, so I can't read this top part. Ratios compare the relative size of two quantities that I refer to as thing one and thing two. When I say I mean them, this worksheet. So apples and oranges, thing one, thing two. Apples, thing one, oranges, thing two. Identifying thing one and thing two is trickier than it seems often, because ratios are presented as single numbers like the birth rate in the US. We talked about the number of births versus people. Number of births would be thing one, the people would be thing two. So what we're going to do is go through most of these, not all of them. What are the two quantities being compared in the following ratios? Be careful not to confuse units with actual quantity. Now, this little sentence right here, be careful not to confuse units with quantity. Since we're just using our own words, I honestly would not care if you confused units with quantity. So I will give that as an example. What is it, the fifth one? Yeah, the fifth one. So the gas mileage of a Subaru Outback is 35 miles per gallon is a ratio, but the quantities are not miles and gallons. Those are units for the underlying quantities of distance and gas. So that's the idea there, that they're saying that the ratio, the thing one and thing two are distance and gas, that you shouldn't write miles and gallons because miles is a type of distance and gallons is a type of amount of gasoline. I kind of disagree with them though. I mean, honestly, as long as you understand the information you're conveying, why can't you call thing one miles and thing two gallons? So I just kind of disregard that really. It's not an issue that's going to come up in the homework or the test, so it's fine. Use your own words, use whatever words you like. All right, this first one, GPA is 2.74. I still can't believe that they don't tell students this anymore. This is a ratio of something we call quality points. Let me actually do the text. Let me see if that'll be good. That's going to be too big. So that's a no. Quality points. Sorry, my handwriting is a little worse on this. As I mentioned, there's no algorithm fixing it. So if that's thing one, and thing two is the number of credits. So quality points are how many A's and B's you've had and how many actual points you get out of it. So like A is worth a 4, but if you have, if it's a 3-credit class, that means you get 12 quality points. Because you get a 4 for credit 1, a 4 for credit 2, and a 4 for credit 3. Don't worry about that one too much. If this was 15 years ago where they were still telling students this, I'd label it more importantly, but let's just move on. Only one US adult in 5 could calculate interest. Now, this problem right here is going to lead to a common theme for like half of these down here. Only one US adult in 5 could calculate interest. This is not saying one adult to 4 adults, so 1 can and 4 can't. This is not a thing one is those who can and thing two those who can't. This is the people who can, so the adults who can calculate interest to all adults. This is a very important type of proportion where we're comparing a part of something to an entire population. So 1 out of 5 can calculate interest. So that means there's 1 adult who can to 4 adults who can't for a total population of 5, which means if there were 10 people, 2 would be able to calculate interest and 8 would not be able to, but that ratio would be 2 to 10. 2 adults who can out of all adults. And then 2 to 10, you could reduce to 1 to 5. If I had 100 people in total, that means 20 would be able to calculate interest, and then there'd be 100 total, meaning 80 couldn't. So this is what we call a part to whole ratio. This is very, very common. And again, it's going to be the answer to like half of these. 13% of the US adults are numerate. So again, it really only feels like they gave us one thing, a percentage or a ratio of people that can do something. So once again, this is the thing one is the people that can or can't do the thing, and thing two is everyone. So it's the adults who are numerate, which means people who are good with numbers. Adults who are NUM for numerate. And then this is all adults again. APR of 6%, this is going to be the ratio of interest to balance. This is actually a rearrangement of the interest in dollars as a product of the periodic rate times the balance. This would just say that interest divided by balance is APR. So it's just an algebraic rearrangement of equations, so I went ahead and gave you that one. Speed is 75 miles per hour. The word per means the next thing is the bottom of a fraction. It would be thing two. So one person might say, and I'll do this in blue because this is technically breaking the rule above, but your teacher says he doesn't care. Miles could be thing one, and hours could be thing two. Or you can be more specific, and instead of using units, use the quantity. Miles is a type of distance, and hours is a type of time. So the red words are a little more a little more better, a little better. The blue is a little more generic because I could say, instead of miles per hour, I'd say kilometers per second, feet per day. I could make any two word choices for distances and times. It's, of course, best to use the two they use, but I could still arbitrarily switch the miles to kilometers and it doesn't change anything about it. It would just be weird. Half of 17-year-olds don't know enough math to work in an auto plant. Half of 17-year-olds don't know enough math to work in an auto plant. So since they used the word don't this time, instead of saying the people who can to the total population, we say those who can't. So the 17-year-olds who can't, ... I don't have enough space to be able to write all that, who can't do enough math or don't know enough math, to all. Now, it's not all people, it's all 17-year-olds. That looks like a 117-year-old. All 17-year-olds. There we go. I'm going to skip a couple of these. I might leave them for discussion boards. Again, I'm making that decision at the end of class, so hold on, don't leave early, or come back and watch later. We're going to skip this one. You borrow 300 and you pay 350. This one will be principal to New Balance. The 350 being the New Balance, the 300 being what you borrowed, the principal. These finance ones, I just wanted to go ahead and get out of the way. 52% we're going to skip. 15.5 we're going to skip. The 50.3 we're going to skip. The last one we're going to do. Apple Incorporated reported 9.21 earnings per share in 2017. Apple is an awesome growing company. Sure, they just had a little hiccup a few days ago in the stock market because of lots of reasons we don't need to get into. But I can almost guarantee they'll grow again. I mean, they've already gained some steam back. It's not just Apple, it was everyone in tech. Not the point of this, I'm rambling. So what this one is, they talk about reporting earnings. Then they use the word per, so the next thing would be the second thing. So the number of shares. Once again, the word per means the next thing is the bottom of a fraction, or it's the thing to, however you want to say that. So I'm going to label this A, B, C, and D. Again, these will be for the discussion board, question mark, if I assign it. But let's hold off on that idea for now. And that's page 64. All right, so I need to clear the screen. Let's come off of this. There we go. All right. Lots of space. Nope, not there. Lots and lots and lots and lots and lots of space. So what you're going to see a lot in this class is going to be a proportion table. If my audio is going in and out, I have a feeling my internet is having a problem again. I had a class, was it Thursday maybe, that it just kept cutting out and I had to record everything in multiple parts. I'm hoping that doesn't happen. So fingers crossed that it's going to keep working. If it crashes, we'll have to deal with it and just hang out, and I'll be back as soon as I can. Hopefully it doesn't crash. Proportion tables. This is something that you're going to see throughout this chapter as well as the next chapter. You'll see homework problems on this. You'll see test problems on this. You're going to be dealing with a lot of things called CPI, consumer price indexes, that'll use these. And you can be given these types of problems in giant, massive tables. And I will draw up an example in a giant, massive table after we do a simple table first. But when you're using a table, you need what I call 3 corners of numbers and a blank. You need 3 corners of numbers and a blank. These corners do not have to be all sitting next to each other, but you should be able to draw one box around all four, i.e., you need all values in just 2 rows and 2 columns, but it doesn't matter where those rows or columns are. Now that might not make a lot of sense without seeing the examples. We're going to see the examples and get it to make sense. Don't worry. So let's start out with a small one. And we're going to do apples and oranges. So I could have given you a problem. And I'll also draw it up as a table. But else I might say, all right, a store sells 2 apples on Monday, sells 2 apples and 3 oranges Monday. On Tuesday, store sells 6 apples. If there is a proportional relationship in the fruits, how many oranges sold Tuesday? This is the type of example you can see with this. Now, I've given this to you as a word problem, but I could have also just given it to you as a table setup. So I'm going to take the word problem and I'm going to set up the table, but just know that in your homework, they might just go ahead and straight up give you the table without the word problem. You have to be able to handle this both ways. So, thing 1, apples. Thing 2, oranges. So we're going to go apples over oranges if we wanted to just go ahead and do this straight up. So apples over, I'm going to abbreviate it, oranges. So that's the proportion I'm choosing, which means on Monday, that's the first side of our proportion, 2 apples and 3 oranges sold. So it's 2 over 3, 2 apples, 3 oranges. Apples are in the top, oranges in the bottom. Consistency. Then we set it equal to the other scenario. On Tuesday, the store sold 6 apples. So that's a 6. Apples, why do I know the 6 is the top? Because apples go in the top. How many oranges were sold if this is proportional? So we were told this is proportional, which is why I've chosen to set up this fraction equal to a fraction. We don't know how many oranges were sold, so give it a letter. Give it X in O if you want to be a little bit of a pain, because O looks like 0. Not my favorite letter choice, but you could do it. You're going to take this and you're going to CM, which stands for cross multiply. So we take the 2 times the X and the 3 times the 6. Here's the 2 times the X. You set it equal to the 3 times the 6. And that's 3 times 6 is just 18. So we get 2X is equal to 18. We went over how to solve an equation like this last time. You divide both sides by the number paired with your variable, divide by 2. And what you get is that X is equal to 9. Now, let's say you just box this up and ship it out in the real world. You say 9. That's not an answer. 9 is not an answer. You need to be asking yourself, what is X? X was the number of oranges sold on Tuesday. So it was 9 oranges. That looks like a T. Come on, undo work. 9 oranges on Tuesday. That is a quantitative reasoning answer. 9 is not a quantitative reasoning answer. 9 oranges would be good enough since they said specifically on Tuesday, but this is being very specific. 9 is not an answer. Now in my math lab, they generally have those words set for you already, so it's not really an issue, but remember, we're quantitative reasoning students because we're trying to take this and use it in the real world. We have to be specific, we have to use our words. Does that make sense? Well, Monday, it was 2 apples and 3 oranges. If this is a proportional relationship, that means if the apples increase, so should the oranges, and they should be increasing in a similar manner. Now, I haven't described what that similar manner is yet, but we will shortly, probably today, maybe today, maybe next class, we'll see, but I'll tell you the specifics sooner than later. So 2 apples went up to 6 apples, so the apples went up. 3 oranges went to 9 oranges, they went up. So as far as we know for now, that makes sense that they're a proportion. Now you might say, well, the apples went up by 4 and the oranges went up by 6. Those aren't the same number. But that's not what proportional relationships are. It's not saying that they increase exactly the same. It's that they increase with a constant ratio to each other. What it means is it's a constant multiplier. So that's kind of a hint as to what grand statement we'll have sooner than later. All right, so here's the problem set up as an official word problem, but alternatively, I could have just said the following table is a proportion. So here we have a proportion table. And I say we have apples. Hold on, give me 10 seconds. All right. Don't want to do there, a little lower. We have apples and we have oranges. And we sold some apples on Monday, we sold some apples on Tuesday, we sold some oranges on the same days. So 2 apples and 3 oranges on Monday, and then we sold 6 apples on Tuesday, and this spot is blank. Let me pull back, there we go. So this is a proportion table. This is how it could have been set up as well. So same exact numbers, same exact answer, just a different setup. When using a table, you need 3 corners of numbers in one blank. These corners do not have to be sitting next to each other. They are in this instance. I'll give you an example where they aren't next. But you should be able to draw one box around all 4 of these. And then that's what I'm talking about with the corners. You're going to draw a box, your own box around this somewhere. So like this would be me drawing a box around some numbers. And the goal is to draw that box so that 3 corners have numbers and 1 does not. This has a number, this has a number, and this has a number. So that's exactly what I'm referring to. So when you have your table, you're supposed to imagine yourself drawing a box. Some people like to draw it, some people just imagine it, some people ignore me and do their own thing and get them half wrong or all right, depending on their skill level. But this is us drawing a box in such a way that in this box, this 3 is in a corner, this 2 is in a corner, this 6 is in a corner, this blank is in a corner. Now you might say, well, obviously they're corners because of this scenario. It'll be a little more complicated next example. So 3 of these are numbers, 1's a blank. We can make a proportion out of this. Now here is the beauty of proportions. You can set these up 8, arguably 16 different ways and still get the same answer. I've already alluded to this fact because I said you could go apples over oranges or oranges over apples. It would have flipped this thing upside down. And when you cross multiply, you can't even tell anymore that you flipped it upside down. You'd get the same answer. So all we got to do is just make a fraction equal to a fraction using these numbers, either going top over bottom equals top over bottom or left over right equals left over right. It's again, you just need to be consistent. So I'm going to show this a couple different ways. The first one I'll show is my favorite way. So my favorite way would be to go just set these numbers up as a fraction equal to fraction exactly as they look. 2 over 3 equals 6 over x. Top left over bottom left equals top right over bottom right. This is the easiest way in my opinion. I find it easy because the numbers are laid out in the proportion exactly as they are in the table in terms of their corners and positioning. This is exactly the same equation we just solved earlier. You cross multiply, you get 2x equals 18. You divide and you get x equals 9. The same answer. X being here. Wherever your blank is, you call it x. Or N or J for oranges, whatever letter you like. Here's an alternate way. Some people, and for some reason the guided worksheets really like to do it this way, they'll go from left to right. So they'll compare the apples, 2 over 6. So that was Monday to Tuesday. So for the oranges, you just have to be consistent. Monday to Tuesday, so 3 over x. Cross multiply, you'll get 2x equals 6 times 3, which is 2x equals 18. Clearly the same answer. Now, and I'm going to do this in orange since I got a lot of red on the screen already. A wrong way. Again, there is 8, arguably 16 different ways to take these 3 numbers in a variable to set up a fraction equal to a fraction and get the answer right. Instead of going 2 over 6 equals 3 over x, I could have gone 6 over 2 equals x over 3. I could go from right to left. Instead of going top over bottom, I can go bottom over top. 3 over 2 equals x over 6. After you cross multiply, that orientation is no longer visible. But you can still do this 8 or 16 ways wrong if you're just doing this, not paying attention. Because again, consistency is the key. Going left to right, top over bottom, or right over left, however you wish to do it. Doing this wrong way is maybe, all right, I'm going to go apples over oranges for the 2 over 3. I go top left over bottom left. But then on the other day, I flip it. I go x over 6. So I went top over bottom on the left and bottom over top on the right. That's inconsistent. So what you'd end up with is 2 times 6 is 12, and 3x. Dividing both sides by 3, you get 4 equals x. Remember, when you get these answers, you're supposed to be saying, does it make sense? What is this? This was oranges, so 4 oranges. Does it make sense? Well, the apples went from 2 to 6. They went up, I would say, significantly, whereas the oranges went from 3 to 4. There were more oranges to begin with, and the increase was smaller than the apples, of which there were less of. So no, this does not make sense. If there were more oranges on Monday, if the apples go up, there should be more oranges than Tuesday's apples. See, the apples went from 2 to 6. The oranges were bigger than the apples, so they should still be bigger than the apples. 4 is not bigger than 6. We did this wrong because we were inconsistent. So this was a simple proportion table because there were no gaps. Again, these instructions say these corners do not have to be all sitting next to each other, as long as you can draw that box around 4 corners where 3 of them have numbers. Now, when I say box, I mean a box. I don't mean something that looks like this. That's not what I mean. You have to draw a rectangle. It can be a tall rectangle, it can be a wide rectangle, it can be a perfect square, but you can't zigzag. It has to be a quadrilateral box. So let's see the large and in charge example. And we're going to have a whole bunch of things. Let's go oranges, bananas, kiwis, watermelon, apples, limes, lemons, and then a fruit. I feel like he's kind of gotten lost in the history of things, tangelos. Those little small oranges, they're like a half orange, half tangerine. And then we're going to have a whole bunch of days for these. We're going to go full week. I'm going to abbreviate the days, though, because this will get ridiculous otherwise. Monday, Tuesday, Wednesday, Thursday, which we're college students, we should know is R, Friday, Saturday we'll do SA, Sunday we'll do SU, and then just finish the horizontal lines. Big table, big table. Give you a second to do that. Okay, so not giving the actual word problem where we say on Monday the store sold 7 oranges, on Thursday they sold 1 orange, on Sunday they sold 11 bananas, for kiwis they sold 2 on Tuesday and 6 on Friday. For limes they sold 3 on Tuesday. Then for tangelos we sold 100 on Wednesday, and lemons we sold 12 on a Saturday, excuse me. So what we're going to do here is we're going to find the only value we are able to if all these are proportional. So yes, the store sold some oranges on Tuesday, Wednesday, Friday, Saturday, Sunday, bananas on the days we're missing, whatever. Maybe one or two of these were zero, but I didn't want to fill out this table entirely because then lots of answers would be findable, excuse me. So we are going to find the only value that we're able to if all of these are proportional. So only one of these is findable, I believe. I believe I drew that up correctly. Yes, we're good. And you might think otherwise, but we're going to draw a whole bunch of different boxes and we'll ultimately find the one that works. But we'll do them wrong first. So here's the reminder. We'll be down back there in a second. You need 3 corners and a blank. These corners don't have to be sitting next to each other. You can skip rows, you can skip columns, but you should be able to draw one box, one quadrilateral, 4 corners, around those, where 3 of them would be numbers and 1 would be a blank. And again, the real tried and true idea here is that you need values along 2 rows and 2 columns. It just doesn't matter where those rows or columns are. So I'm going to draw some boxes that are bad at first. Warning. So some people might say, all right, I can do a box right here. So here's a box. This is a bad one. So this is me drawing a box where the corners are here, 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 and here. Those are the corners. So this blank row, we're ignoring this. We don't even think about this for the idea of proportionality or setting up that fraction equal to a fraction. But this box that I've drawn with the corners circled, 2 are numbers and 2 are blanks. If we wrote this out as a fraction, 7 over x equals y over 2, because these two things are different, you can't make them the same variable, that would not be a solvable equation that would give us a value. That's why it's important that when we draw that box, 3 of the corners need numbers and 1 of them needs to be blank. So that box fails. All right, so what you might say is, all right, well, here's a number, here's a number, here's a number, here's a number. Maybe I could do it like this. Would this work? So now I've got a box, and inside of this box, there's 3 numbers. But are the 3 numbers on corners? The 7's a corner, that's fine. The 1's a corner, that's fine. This 2 is not a corner, though. This blank is a corner, and this blank is a corner. So that won't work either, because blank, blank, we can only have 1 blank to make the fraction equal a fraction scenario. So that fails as well. I said I'm going to draw a bunch of bad ones first. All right, maybe someone thinks this works. So, like I said, a lot of people just think you got to get 3 numbers in the box. This is actually the worst one so far. This is the corner of a 3. That's fine. But blank, blank, blank. Sure, the 112 are in there, but they're not corners. This is awful. That's 3 over x equals y over z. There's no way you're finding out what those numbers are. So that was a bad box. Some people might say, well, try just doing the whole entire thing. Definitely doesn't work. Number, blank, blank, blank. That fails. Hmm. 2, 6, 3, 100. Maybe people are starting to kind of hone in on these. Maybe they do something like this. Would this work? Question mark. The 2 is in a good position. The 6 is in a good position. The 100 is not. Blank, blank. But the fact that the 2 and the 6 are on a completed row, or both in corners along a row, and then there's another number in the same column as the 2, this is a hint as to what you should be looking for. You want to look for a row or column where there's 2 values, and then find another number in this opposite row or column. So what I'm saying is, here's 2 numbers in the same row. If there is a number in either of their shared columns, so either another number in Tuesday's column or Friday's column, you can make a box out of it. And look at that, there's 1 for 3. Or maybe you notice that 2 and 3 are in the same column. So you'd say, all right, well, if there's another number in the same row as one of these, either the kiwi row or the limes row, then you can make a box out of that. And sure enough, there's a 6 there. So the 2, the 3, and the 6 are going to be our ultimate box. Let me go with that idea again before we draw it correctly, though. Maybe you notice, oh, 7 and 1, these are in the same row. So you say, well, these could be 2 corners, but then you need a number either in the Monday column or the Thursday column. All of these are blank, all of these are blank, so you can't use the 7 and the 1, at least in that regard. You might say, actually, that's it for all the different scenarios, because the 12's in a column by itself, that won't work. Row by itself won't work. 100 row column by itself. So you see the 2 and the 6, that might have been a good hint. And then you say, hey, that 3 is in the same column as the 2. Excuse me. I was focused on my going too far there. There we go. That's better. Boom. This is the correct box because we have 3 corners with numbers and a blank that we can call X. Now, I actually chose these numbers exactly as the same as the apples and orange problem as before, so that you already know what the answer should be. What that tells us is that we get 2 over 3, so corner over corner. So I went top over bottom, so be consistent, top over bottom, 6 over X. But again, there are 8, arguably 16 different ways to set up that proportion to ultimately get 2X equals 3 times 6, 2X equals 18, divide by 2, and you get X equals 9. So that would be 9 limes, because that's where X is, on Friday. So in the previous example, the 2 and the 3 were talking about apples and oranges. Now I've made them kiwis and limes. So that's why this is not going to be oranges anymore. This unknown was in the limes position. I did that intentionally, just to keep us on our toes. I didn't need any, there could have been numbers here. 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 You don't use them. You are able to skip rows. You are able to skip columns. This is a common theme in this course. Lots of homework, test questions, guided worksheet questions. This is going to be a common theme. It doesn't matter how far these rows or columns are separated as long as you can draw a box out of them. Now, what happens a lot of the times is once you get this corner, maybe that would enable you to find another one. So now I've got these 2 here. Maybe there's another number I could then find, but there isn't for this example. I did make it so there was only one value you'd ever be able to find. But in our guided worksheets, we will see that finding one can get another, then get another, and then get another, and maybe even complete a whole table if this chain effect is functional enough. There can be multiple ways to find a box, especially if you've got more numbers up here. It's not always just one way. It's just this example, I made it so there was only one way. All right, and that is it for the notes to share. Let's go back over to the guided worksheet. So using ratio tables, page 65. Here we go. Guided activity 1. This is a ratio or proportion table. It's actually got a similar theme to that kind of original US versus Mexico birthing rate population problem. So they say the number of US births in 2017 was 3.8 million. Is this a lot of births? To make sense of this statistic, we can make comparisons to the US population of 324 million people in 2017, and then compute the birth rate per 1,000 people. This is the third or fourth time I'm reminding you of this. The word per means the next thing is the bottom of a fraction. So given a fertility rate of 60.2 births per 1,000 women aged 15 to 44, so they're saying that this is the general childbearing age. Yes, we are all aware that childbearing age can be younger and older than this. They're just saying on average. So they're only, for one of these statistics, they're only looking at the women aged 15 to 44. but they tell us that there's a fertility rate of 60.2 births per 1,000 women. Rates are ratios. We'll be studying them more explicitly in later sections. But what we can do is work backwards and actually compute the number of childbearing women, just given this information and the fact that all these things are proportional values. So what they do initially is they organize everything in a table. So we have a column for births based on the total population, based on only a population of 1,000 people. So this is us scaling the population down to 1,000. This is a very common theme. I talked about earlier scaling something to 1. This is the same idea, except instead of writing the number 1, you write the number 1,000. So we know there was 3.8 million births for the total population of 324 and some change million people. What we will want to find out ultimately after a little bit is how many women of childbearing age were there, how many births were there per 1,000 people of the regular population, and you'll see that there's no letters in this spot or this spot, so they don't actually want us to find those. But it is 60.2 births per 1,000 people. I'm not saying we can't find them, I'm saying they don't want us to find it. Now, before we actually go and do it with those numbers ultimately, let's keep this simpler and let's just do a different problem. So we will come back to that, but for now, let's start with easier numbers to get a feel for the solution technique and see if we can have things make sense to us. So instead of saying it's 3.8 million births for 324 million people in America, we're saying it's 4 births for 500 people in some random population. There's only 500 people in this population, and out of them, there were 4 births that year. So we want to find out how many births there were if we scaled this population to 1,000. And this is where that idea of the common multiplier will come into play. If you double the population, what do you expect the births to do? That's the idea of proportionality. If this population doubles from 500 to 1,000, what do you think would happen to the number of births? So that'll be a massive spoiler when I answer it. We also want to find the number of women that are in childbearing age based on, okay, well, it's 4 births for a population of 500, but it would be 12 births if there were 900 women childbearing age. Now, this proportion table is set up so that we can find both of those blanks with 2 goes. So I'm going to draw up, actually before I annotate, let's zoom in a little. There we go. So I can write cleaner. So the idea is we want to draw a box in such a way that in that box, 3 corners have numbers and 1 of them has a blank. Well, if I drew my box this way, that maybe this is right, maybe this is wrong. Don't draw these boxes around labels, only the numbers in the table. Never, ever, ever draw the boxes around the labels, births, population, women. I'm not going to draw the box around that. They're labels, not numbers. You can't use them. This box won't work because this is a blank and this is a blank. So 2 blanks, 2 numbers, that would fail. So let's try again. Maybe you want to do it this way. Like I said, I'm going to do it wrong a couple of times because that's what you would do probably. All right, we got a number in a corner, we got a number in a quarter, but this is blank and this is blank. 2 blanks, can't do it. So clear. How could I tackle, because I can do this one or this one first. I don't have a necessary order for this. I can find this first and then the women, or I could find the women and then the births per 1,000. So I'm going to try and tackle the women. My goal is to have this box be a corner, and since it's in the top right, I'm definitely going to have to draw the box like this. Now, if I drew it here, if I finish the box like this, is this right or wrong? 1 number in a corner, blank, blank, blank. Definitely not it. So clear the screen. What if I did this? I got 2 numbers in corners, but 2 blanks. So nope, that's not it. What if I put my box around all of the data? The entire table except for the labels. Number, 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 blank. That's what we need to do. So my red ink, let me squeeze that in over here. And again, I like to do top over bottom, so I'll go 4 over 12. is equal to x over 900. So I'm going to call this an x. Number, variable, perfect. We can cross multiply. So we'll get 4 times 900 is equal to 12 times x. 4 times 9 is 36. So that's 3600 equals 12x. We will then divide both sides by 12, which will give us 12 will go into 36 3 times, so that's 300. So 300 is equal to x. So that says there are 300 women of childbearing age out of this total population of 500, thus leading to 4 births that year. So you can say it's 4 births per 500 people, or 4 births per 300 women of childbearing age. So that's one of the blanks. In blue ink, I will do the other one. So I'm going to try and draw a box in such a way that I can find this blank. Let's call this Y. So we're going to call that Y. That's the corner we definitely need to be using. I'm going to draw a couple bad boxes. This would be a bad box because we got, if we do it this way, blank, number, blank. 2 blanks is a problem. So let me undo. If you try and do it this way, you'll have blank, number, blank. So that's still bad. Can't do it that way. Maybe this way. Remember, don't go over the label sections. Number, blank. Perfect. So that gives us our equation. I can go 4 over y is equal to 500 over 1,000. Cross multiplying, you'll get 4 times 1,000 is equal to 500 times y, which is 4,000 equals 500y. Divide both sides by 500. And basically you're just doing 40 divided by 5, which is 8. So 8 is equal to y. Y being the number of births per 1,000 people if the population doubled. So this was us scaling the population to per 1,000. So if there's 4 births per 500 people, that means there's 8 births per 1,000 people. Notice that this value is double the previous one. The 500 doubled to 1,000, the 4 doubled to 8. That right there is the ultimate concept of 2 things being proportional. If one thing doubles, the other must double. You will hear me say this again. I will officially write it in the notes next class. But that's the idea. The idea of 2 things being proportional means that if you were to double one, the other doubles. You could extend that. You could say if one triples, the other triples. If one halves, the other halves. But it means that there's a constant multiplier between them. So if one of them goes up 10 times, the other goes up 10 times its value. So if something went from 10 to 100, then the other would go from, say, 50 to 500. That's what it means to be proportional. Not only do they increase together, it means if one doubles, the other doubles. Okay. I'm thinking we'll call it a day there. So we haven't finished this section. What we'll do next time is go and complete that original problem, but instead of having nice, easy, pretty numbers like 4, 12, 500, 1,000, and 900, we're going to go back to having numbers of 3.8, blah, 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 million, 324, blah, 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 million, 60.2 births per 1,000 of women of birthing age, scaling the population to 1,000. Once again, scaling a population to 1,000 is a pretty common tactic. You might say, why not 100? 100 is great as well. When we scale things to 100, we tend to think of them like a percentage. We like to scale things to a 1,000 because then we can knock out basically a collection, a comma collection. We can turn numbers that were in millions to thousands, or numbers that were in billions to millions, or numbers in trillions to billions. it doesn't affect how we say the number nearly as much. But we'll see all of these things. We'll see scaling to 1, we'll see scaling to 100, we'll see scaling to 1,000. Those are the 3 most common that we see in the real world, as well as this course. It's not to say you can't scale it to some random number like 17 or 38.7. It's kind of weird and wacky to do so, but you could. So
that is where we're going to close shop today. So we made some pretty good progress in 2.1, but as I said, we did not quite finish it, which is why the homework is not going to be due in 1 week. We will assign it officially next time, but you're more than welcome to go ahead and begin that homework. But for now, focus on whatever on the board you haven't finished yet. All right, so we will begin, I think we'll begin 2.2 next time as well. We still have a decent amount of 2.1. We might not get to 2.2, but go ahead and just put your eyes on the notes to share for 2.2, as well as the textbook that's going to be on the weighted average, which is a really, really, really important formula that you can use to calculate your grades for lots of courses, and not just that, lots of other things as well that we'll talk about when we get into it. But again, we'll be diving into more of 2.1 first. So my math lab homeworks, we got 3 sections on the horizon, 1 due today, 2 Excels, 1 of them due today, a discussion board in case you haven't done one or done this one yet. And then remember that if you do miss this one, just make sure that you absolutely participate in the next one, because if you miss 2 in a row, you get double zeros, because not all discussion boards will have infinitely many answers. We will have some though. All right, so we'll see you on Wednesday, the 2nd? For more of 2.1. All right, if you have any questions, make sure you email me, and have a good day.